I'm Kevin Kurtz. I'm the VP of Engineering for Quadrant Solutions. Let's talk about how to design the size, shape, and material selection of your magnet. So the size and shape are going to determine the magnet's actual output as well as the material properties involved. The material has a property called BR, or it's residual induction. And that lets us determine what's the most flux density at any point the magnet can produce. If it was infinitely long, infinitely large, we could produce BR out of the magnet, but that's not actually what we're getting when we build the magnet. We're actually sitting somewhere on what we call the BH curve of the magnet. The output is determined by the size, shape, and circuit. So how do we determine what size and shape we need? For determining the permeance coefficient of a magnet, that is where it's sitting on our magnetic material curve, our BH curve, the second quadrant curve of magnetic properties, we're going to take into account the size and the shape of the magnet. The two factors you're going to look at there in a rectangular prism, a box-shaped magnet, are going to be the surface area of the pole, so the cross-sectional area of that magnet, and the thickness and the direction of magnetization. The surface area is going to be in the denominator of that equation, and the thickness is in the numerator of the equation, which means as the thickness gets larger, the flux output at each individual point is going to be larger. We're going to sit higher on the curve. As the surface area of the pole gets larger, the individual or average flux density across the face is actually going to decrease. Does that mean the whole flux output of the magnet is going to decrease? No, not necessarily. As it gets larger, it's going to sit lower on the curve, but that's at each individual point. We have to integrate across the whole surface to determine the total flux output. But this is why you have to factor in shape and size into the calculation of what your magnetic output is going to be. This is also a different calculation for cylinders, otherwise known as discs, or ring magnets, an ID-OD magnet, or an arc-shaped magnet. So we're going to put the magnet in the worst case scenario in simulation software or in a hand calculation and try to determine how much coercivity, how much opposing field we can take, both from our internal self-demagnetization field of the magnet and from the outside environment and temperature, and determine which coercivity grade of magnet is more relevant to your situation. We have many. In sintered Indy FEB, we can go all the way from straight grades, H grade material, all the way up to AH, EH, UH materials. There's a large band of coercivities allowing us to go anywhere from a maximum of 60 degrees C all the way up to about 220 degrees C in sintered Indy FEB. We have engineering services to help customize these magnets. They can be made to your shape, size within the boundary conditions we talked before. We can ramp up very quickly. We mass produce these. We can make millions and millions of them at a time, or small sample quantities if you need. We can help do engineering, design, FEA, any simulation needs, full engineering support.